Hi viewers, a warm welcome to all. This module is intended to discuss the applications of nanomaterials. Nanomaterials manifest extraordinary, charming and beneficial properties. They have a unique, beneficial, chemical, physical and mechanical properties which can be exploited for enormous applications like laptop chips, better insulation materials for the development of phosphors, low cost flat panel display systems, for cutting tools, batteries, excessive power magnets, high sensitive sensors, long lasting satellites, long lasting medical implants and application still continues. Since applications are many, in this module, we are limiting our discussion to 3 important applications of nanomaterials. They are nanoelectronics, nanosensors and nanocatalysis. Our discussion is limited to these 3 applications in this module. First of all, nanoelectronics. Nanoelectronics is the term used in the field of nanotechnology for electronic components and research on improvements of electronics such as display, size and power consumption of the device for the practical use. Nanoelectronics includes research on memory chips and surface physical modification on the electronic devices. Nanoelectronics cover quantum mechanical properties of the hybrid material, semiconductor, single dimensional nanotubes, nanowires and many more. Nanoelectronics aims at improving the capabilities of electronic devices and displays while shrinking them and reducing their weight and power consumption. Well developed nanoelectronics can be applied in different fields and are especially useful for detecting disease causing agents and disease biomarkers. Different approaches of nanoelectronics. First of all, nanofabrication. Nanofabrication can be used to construct ultra dense parallel arrays of nanowires. Silicon nanowires are being increasingly studied towards diverse applications in nanoelectronics, energy conversion and storage. The second approach is nanomaterials electronics. It allows more transistors to be packed into a single chip such that the size can be greatly reduced. The uniform and symmetrical structure of nano system allows higher electron mobility and symmetrical electron hole characteristics. Next approach is molecular electronics. These schemes would make heavy use of molecular self-assembly, designing the device components to construct a larger structure. Other approaches include nanoionics, which is the study of the transport of ions rather than electrons in nanoscale systems. Nanophotonics studies the behavior of light on the nanoscale and has the goal of developing devices that take advantages of this behavior. Nanoelectronic device is other area of today's discussion. Nanoelectronic device include computers, memory storage, novel optoelectronic devices, displays, quantum computers, radios, energy production and medical diagnosis. Let us enter into the details of this. First of all, computers. Nanoelectronics enables computer processes more powerful than that are possible with the conventional semiconductor fabrication techniques. Memory storage. Nanoelectronics enable the generation of ultra high density memories. Novel optoelectronic devices. Nanoelectronics helps in the development of high performing optoelectronic devices. Two promising examples for such materials are photonic crystals and quantum dots. Display systems or displays. The resolution of the display devices can be significantly improved by synthesizing nanocrystalline phosphors, while considerably bringing down the manufacturing cost. This is highly cost effective. Quantum computers. Such devices enable the use of fast quantum algorithms. Quantum computer has quantum bit memory space termed as qubit. Then radios. A nano radio, also called carbon nanotube radio, is a nanotechnology device acting as a radio transmitter and receiver by using carbon nanotubes. Energy production. Research is ongoing to use nanostructured materials to create cheaper and more efficient solar cell than are possible with conventional planar silicon solar cell. Sunlight energy harvesting is very important, hence the solar panels are more important, and this nanomaterials intervention leads to the production of highly efficient solar cells. Medical diagnostics. Nanoelectronic devices can detect the concentrations of biomolecules in real time for use as medical diagnostics. Next part of today's discussion is nanosensors. What are nanosensors? They are devices that can detect and sense certain signals. The signal could be biomedical, optical, electronic, electrical, physical or mechanical signals. A sensor is simply a transducer that converts a measurement, that is a quantity or a parameter, into a signal. That signal carries information. The picture is the block diagram of a sensor or sensoric application of nanomaterial. We have an analyte linked to sensor. It is then linked to transducer, detector, and there is a connection between, feedback between detector and the sensor. Human senses. We all familiar with human senses, sense organs. Any biological sensory point used to convey information is a sense organ. Sense organs, human sense organs shown here. Eyes used to sense light. Ears can sense sound as well as make some balance in the human body. Nose which senses smell. Tongue senses taste. Skin for sensing temperature, pressure as well as temperature. Now what are nanosensors? Nanosensors are nanoscale devices that measure physical quantities and convert those quantities to signals that can be detected and analyzed. There are tiny sensors in the size of few nanometers, that is about 10 to 100 nanometer. These nanosensors can detect the presence of nanomaterial or molecules in the size and even smaller. Definition of a nanosensor: an extremely small device capable of detecting and responding to physical stimuli with dimensions on the order of 1/1000th of a meter. Physical stimuli means biological, chemical substances, displacement, motion, force, mass, acoustic, thermal and electromagnetic stimuli. Characteristic features of nanosensors. Nanosensors have high sensitivity and specificity over sensors made from traditional materials. Nanosensors can be integrated with electronic devices or nanoelectronics to add native processing capability. Nanosensors offer significant advantages in cost and response times, which make them suitable for high throughput applications. One-dimensional nanomaterials such as nanowires and nanotubes are well suited for the development of nanosensors. Potential applications of nanosensors include medicine, detection of contaminants and pathogens, and monitoring manufacturing process, and also for transportation systems. Let us check what are different type of nanosensors. On a broad scale, nanosensors can be divided into 4 types. Each have subtypes also. We are here considering the major types of nanosensors. They are optical nanosensors, biological nanosensors, chemical nanosensors, and physical nanosensors. Nanosensors, different types of nanosensors are shown in this tabular column. Optical nanosensors, biological nanosensors, chemical nanosensors and physical nanosensors are the major category. Their subtypes are shown at the bottom portion of every type. Optical nanosensors may have proximity sensors or ambient light sensors as subtype. However, for biological nanosensors, it may be antibody-antigen interaction sensors, DNA interaction sensors, or enzymatic interaction sensors. Chemical nanosensors can sense or understand chemical composition as well as molecular concentration. Physical nanosensors are very important and they can sense parameters such as pressure, force, mass and displacement. First of all, optical sensors. Proximity sensors we are considering. Proximity sensors are designed for use in detecting the presence of an object or motion detection in various industrial, mobile, electronic appliances and retail automations. Examples of proximity sensor usage include the detection of an out of paper condition in a printer or a mobile phone screen that aims to save battery life when placed near a face. Ambient light sensors. They provide precise light detection for a wide range of ambient brightness and are commonly used in LCD backlight control in mobile phones, LCD TV panel and notebook applications. One way to convert optical signal is by using electro-optical sensors. Ambient light sensors is nowadays incorporated in many laptops. Biological nanosensors. Bio-nanosensor or a biological nanosensor is an analytical device incorporating a biological or biologically derived sensing element. Biosensors for bio recognition element, molecular, cell based or tissue based. It is then there is a transducer device. Transducer may sense optical, mechanical or electrochemical signals. Analogy between human sensing system and artificial sensing. Human sensing is natural sensing, but nanosensors are artificial sensors. Let us compare the human sensing system with the artificial sensing system or nanosensing system. In human sensing system, sensor receptor is taken up by sensory nerve and the signals are processed by the brain. However, in artificial sensing system, the sensing element or receptor is taken up by transducer, which is then picked up by analog circuit, and the computers will process the signals to get an output. Chemical nanosensors. Chemical sensors or chemical nanosensors usually contain two important basic components connected in a series: a chemical recognition and a physicochemical transducer. In the majority of chemical sensors, the receptor interacts with the analyte molecule directly. As a result, the physical properties are altered in such a way that the appending transducer can gain suitable electrical signal. General structure of a chemical sensor. This is sometimes referred as electronic nose, which can sense explosives, biochemical warfare agents, gases, toxic gases like oxides of nitrogen, then hydrogen, ammonia, carbon monoxide, etc. This chemical nanosensor or electronic nose consists of transducer, a chemical sensor chamber which detect the presence of so-called substances, and finally converted to an electronic signal which can be further processed. Physical nanosensors. Physical nanosensors sense environmental physical changes, including force, acceleration, flow rate of substances, mass, volume, density and pressure. Carbon nanotubes can be used for the development of physical nanosensors. Now, we can enter into applications of nanosensors. Enormous applications are reported. For the sake of the present discussion, important applications are correlated in the diagram. These include nanosensoric applications include food safety, medicine, biomedical research, drug discovery, defense and environmental monitoring. The last area of today's discussion is nanocatalysis. Nanocatalysis is a rapidly growing field which involves the use of nanomaterials as catalyst for wide variety of homogeneous and heterogeneous catalysis applications. We all are familiar with two types of catalysis: homogeneous and heterogeneous catalysis. In homogeneous catalysis, the catalyst and the reactant all in the same phase. However, in heterogeneous catalysis, the reactant and catalyst are in different phases. Nanocatalysis is useful for both homogeneous and heterogeneous applications. Nanocatalysis have combined advantages of both the homogeneous and heterogeneous catalytic systems. Nanocatalytic system allows rapid, means very fast, selective chemical transformations with excellent product yield. High product yield implies lowest amount of byproducts. Because of nano size, that is high surface area, the contact between reactants and catalyst will be high. Insolubility in the reaction solvent make the catalyst mainly heterogeneous and hence separation will be more easy. Also, catalytic recovery is very easy. Catalytic activity of a nanocatalyst. The catalytic activity of a nanocatalyst depends on several parameters. These parameters include geometry, composition of the catalyst, oxidation state of the central metal, physical environment as well as chemical environment. Nanomaterial used as catalyst. There are several types of nanomaterials which proved their applicability as catalyst. Such nanomaterials include CNTs, that is carbon nanotubes, non-metallic oxide nanoparticles, bimetallic nanoparticles which are comprised of two metals, nanoclusters which is the missing link between atom and a nanoparticle, we familiarized it, nanowires, one-dimensional nanoparticle, nanocomposite, nanoporous materials. These type of nanomaterials can perform as catalysts. Some potential applications of nanocatalysis. First of all, dehalogenation and hydrogenation. As the name indicates, dehalogenation represents the removal of halogen from a particular organic compound. Hydrogenation is the process of addition of hydrogen to multiple bonds. Rhodium nanoparticles can catalyze the dehalogenation of aromatic compounds as well as the hydrogenation of benzene to form cyclohexane. Benzene C6H6 on addition of 3 molecules of hydrogen, that is 6 hydrogen atom, converted to cyclohexane, that is C6H12. That is the hydrogenation process. Typically, rhodium nanoparticle can catalyze that reaction. Another reaction is hydrosilylation reaction. The process of addition of hydrogen and silicon across a multiple bond is termed as hydrosilylation. The reduction of gold, copper, nickel, palladium or platinum organometallic complexes with the silynes produces metal nanoparticle that catalyze the hydrosilylation of alkenes. Reaction represents here is a hydrosilylation reaction. Here silicon and hydrogen add across the double bond. Organic redox reactions are another category where we can use nanocatalysis. The oxidation reaction to form adipic acid shown below can be catalyzed by cobalt nanoparticles. This is cyclohexane. It is oxidized to cyclohexanone and cyclohexanol. It is further oxidized to 6 carbon atom containing dicarboxylic acid, that is adipic acid, and for this purpose cobalt nanoparticles can be used. Now we have carbon-carbon coupling reaction. There are several reactions in which carbon-carbon bond formation occurs, and several such reactions can be catalyzed by nanocatalysts. Metallic nanoparticles can increase the rate of CC coupling reactions, that is CC bond formation reactions, such as hydroformylation, the Heck coupling reaction and Suzuki coupling. Palladium nanoparticles were found to be efficiently catalyze the Heck coupling reaction. Potential applications include alternative fuels. Iron oxide and cobalt nanoparticles can be loaded onto various surface active materials such as alumina to convert gases as carbon monoxide and hydrogen into liquid hydrocarbon fuels using an important synthetic procedure called Fischer-Tropsch synthesis. Benefits of nanocatalysis. Several benefits are reported over traditional catalysts or catalysis. The important benefits are nanocatalysis is associated with improved economy, energy efficiency, reduced global warming, which leads to an eco-friendly system. For wastewater treatment, we can use nanocatalysis. Optimum feedstock utilization, safer catalysts and reagents, eco-friendly, minimum chemical waste. Thus, nanocatalysis have profound applications compared to our common catalysis. Future applications of nanocatalysis. We are outlooking the utilization of nanocatalysis in different areas in future, such as petroleum refining, petrochemical industry, synthetic fuels production, for polymer manufacturing and pharmaceutical sector. Nanocatalysis is now trying in the field of food processing as well as chemical sector. Thus, in the present module, we discussed 3 important applications in detail of the nanoparticles. They are nanoelectronics, nanosensors and nanocatalysis. That's all about this module. Thank you all.